Hi, I'm Val Browning, and this is going to be the fast solution to the 2005 MEC 2 problem. And we're going to skip all the review and just get straight to the question. Alright, here's the problem that we're given. Pause the video and take a look. Alright, Part A. Part A asks us to write an algebraic expression for the gravitational force between Saturn and one of its moons. You know from the equation sheet that this is the formula for gravity between two objects. So basically you just set m1 equal to one mass and m2 equal to the other mass, so Saturn and its moon, and you leave your equation like this. It's just basic variable substitution, and this is the answer that would get you credit on the AP. Alright, Part B. Basically for Part B, we're looking to find the equation for the period of the moon as it orbits Saturn. So we know that the force of gravity between two objects from Part A, and we know that net centripetal force equals mv squared over r from memory or from circular motion. And we set these two equal to each other, so we set these two formulas equal to each other. And we get an expression for v squared of the moon, and m2 is the mass of Saturn, not the mass of the moon. The velocity of the moon is also equal to distance over time, and we know that the distance the moon travels, is 2 pi r, which is the circumference of a circle, and it says it's using circular orbits, over the period of the moon as it orbits Saturn. So squaring that, we get 4 pi squared r squared over t squared, and we set this v squared here equal to this v squared here, and solving that equation for t squared using algebra, we get t squared equals 4 pi squared r cubed over g m2, which is the mass of Saturn. And we can either leave this as t squared in terms of t squared, or square root both sides and leave it in terms of t, but I like to leave it as t squared because that'll make it easier later in the problem. Alright, Part C. Which quantity should be graphed to yield a straight line? Conceptually, the reason that it's t squared versus r cubed is because in this equation y equals mx plus b, t squared would correspond to y and r cubed would correspond to x. And the reason we leave m2 in the slope instead of making m2 the dependent variable is because if we want to determine Saturn's mass, which is like it says in the prompt, we can't have our m2 be a variable. Otherwise it's going to be changing, and there's no way to calculate the m2 if it's going to be changing. And we know m2 should be a constant because Saturn's mass is going to be a constant. Alright, so this Part D is basic grid fill-ins, and once you figure out that the proportionality is t squared versus r cubed, you can just square all the values in this column and put them here, and then cube all the values in this column and put them here. If you left your original equation as in terms of t and not t squared, then you could fill this column with just t from over here, and you could fill this column with r to the 3/2 power, which you would get out of the t equation instead of the t squared equation. Alright, Part E, and this is a basic graphing problem. You know that radius is the dependent variable, and you know period is the independent variable, and period is the dependent variable. And you put your scale on there, and you get a line of best fit, and you pick 2 points and you mark them with pluses so that you're going to use for your slope calculation. Alright, so you've got your points for your slope calculation, and now we have to calculate the mass of Saturn. Alright, so calculating from the graph, we have a slope of 1.07 e to the negative 15th second squared per meters cubed. And from our equation, we know that the slope of this line should be 4 pi squared over g m2, because that's everything that's not the dependent and independent variables. So we know that's the slope. So we set the calculated slope from the graph equal to the slope from the equation, and solving for m2, we get 5.532 e to the 26th kilograms. Thank you for watching.